Oh, very good evening, everyone, and welcome to Hibiscus Coast Astronomical Society online chats again. Some of you were here on Tuesday, of course, and listened to Paripi talk about Matariki and the new astronomy school. Today we have got a really good surprise for you. It's Antony Gomez. Antony I've known from my days down in Wellington. He's the president of the Wellington Astronomical Society, and I'm so happy that he's be able to join us today for this talk. If you want to ask questions, if you look just to the right, I think it is, on the YouTube, you'll see the little chat. It says live chat. You can put your questions there, and I will relay them over to Antony. If you have any problems with seeing that, I think you'll probably text someone, let them know, and we can sort that out. Of course, coming up on Sunday is going to be Fraser Kane giving his talk as well. So stay tuned for more of our online meetings. As you know, they're pretty good. So I'm going to hand you over to Antony, who will be taking it away and talking about our place in the universe. And yeah, thanks again, Antony, for doing this.
You're welcome. Hi everyone, it's really good to be here, and I'm glad that James asked me to do this, and I'm really keen to talk about our place in the universe. So this is a talk which, it's the first time I've ever done it actually, is try to give a talk without putting any text or prompts in it. So I'm just looking at pictures and talking to the pictures, so hopefully it'll all go well. Anyway, here we go to the first image. So I hope you all recognize this photo. It's a very famous photo called Earthrise. This was taken on Christmas Eve 1968 from Apollo 8. So Bill Anders took this photo, and with him was Jim Lovell and Frank Borman. Now, what's amazing about this is they are the first human beings to leave the Earth's orbit and go to another world, which is the moon. But they didn't land there. So as they went behind the moon and started to head home to the Earth, they got this amazing view of the Earth rising from behind the moon. So this is quite a remarkable picture, and it's well over 50 years old now. Here's another famous picture. Hopefully you'll recognize this. This is the Eagle on its way to land on the surface of the moon. It's Apollo 11. So this is July 20th, I think, 1969. And yeah, what's amazing about this photo is Mike Collins took the photo. He's the command module person on the command module, and he took this photo. And if you look at it, all the people that are alive on the Earth and alive who have actually lived on the Earth and died on the Earth, and the two astronauts sitting in the lunar module there, is everyone that has lived on planet Earth, essentially. So everybody is on the other side of this picture. So he's the only one missing out of that picture. I'm jumping aside a little bit because I wanted to show you this picture. Here is the Earth, and you can see two bubbles of water there. That is how much ocean water and fresh water there exists on the Earth. So you can imagine the Earth, it's a pretty rocky planet with a layer of water. So even though the Earth contains 75% of the Earth's surface is covered in water, the water only represents something like 0.12% of the volume of the Earth itself. Now, there are actually other water worlds out there. Europa, being one of the moons of Jupiter, has about twice more water on the small moon than there is on the Earth. And Ganymede, another moon of Jupiter, has about 27 times more water on Ganymede than on the Earth, in the form of mainly ice. Europa and Enceladus is a moon of Saturn, contain warm oceans beneath a layer of ice. And this holds a possibility of life existing in these deep oceans and warm ocean. So some of the missions that have been planned now are to go to these moons to actually look for life. There's a better chance of finding life on these moons than there is finding life on Mars. Here's another picture of the Earth with the moon in the background. And what I wanted to show you here is really the atmosphere. If you look at the atmosphere, that's that thin blue layer just above the Earth. That is a thin blanket. And this thin blanket keeps us warm. It has a greenhouse effect. So without the atmosphere, our average temperature on the Earth would be something like minus 15 degrees. But because of the thin blanket of our atmosphere, that gives us a nice comfortable average around 25 degrees. It also protects us from radiation from space and the sun. And also that's where all our weather happens. So we're actually, as human beings, affecting this thin atmosphere by the use of fossil fuels and emissions of other greenhouse gases, and which is resulting in climate change. And some of the effects of climate change is extreme weather, the melting of the ice caps in Antarctica, the heating of the oceans. So there's a lot of effects of the fact that we're affecting the atmosphere. And this is one of my favorite phrases from Carl Sagan. It shows the planet, the Earth there. And what Carl Sagan said is, it has been said that astronomy is a humbling and character-building experience. There is no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. So, I just find that part of this is, we're here, we need to protect the Earth, and climate change is one of those issues. So jumping aside again now, I'm just showing you a picture of the Earth and the Moon, and you can see this is an actual image. And so you can see the distance there. And the average distance from the Earth to the Moon is about 384,000 kilometers. You can see there the Moon actually changes in distance a little bit because it's in an elliptical orbit. And the light traveling from the Earth to the Moon takes about 1.26 seconds. But you could take all the planets of our solar system and put them in that distance between the Earth and the Moon with about something like 8,000 kilometers to spare. So you can imagine that space is really quite a large, it's pretty much empty. The fact that all our planets can actually fit within that distance there. And the Moon itself, we look at the Moon, but the Moon in reality is not that much bigger than Australia. And it's, about 3,500 kilometers in diameter, and Australia is about 4,000 kilometers in diameter. You can fit about 4 moons across the Earth, and you'd need about 50 moons to fill up the volume of the Earth, and about 80 moons to actually have the same mass as the Earth. The other remarkable thing about the Moon is that in terms of the Sun is about 400 times the diameter of the Moon. But by an amazing coincidence, it's also about 400 times further from the Earth. And it means that during a solar eclipse, the Earth and the Moon appear roughly the same size. And that's purely by chance. Eventually, over time, the Moon's going to move further away from the Earth, and we won't get the kind of same stunning solar eclipses that we have now. There'll be more of these ring of fire, annular type solar eclipses, and that's all we'll have. And that, I think, is like about 600 years from now that will start to happen. Here's another phrase by Carl Sagan again, which I love. And this picture was taken by Voyager 1 from about 6 billion kilometers away. It was taken on Valentine's Day, 1990. And what they did there was they took the camera, pointed it in the direction of Earth, and took a photo, and managed to catch a glimpse of the Earth, which is basically just a couple of pixels in this frame. And what Carl Sagan responded is, he said, "Look again at that dot. that's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there in a mote of dust suspended in a sunbeam. So I think that's a kind of a remarkable phrase to capture the Earth. And essentially that sunbeam was a ray of light that was bouncing off one of the cameras and just happened to catch the Earth in the middle of it. Here's another more recent picture. This is from Cassini, which was orbiting Saturn. And again, it took a picture of the Earth from Saturn. So not as far away, because Saturn's only about 1.4 billion kilometers away. But I don't know, does anyone know what this picture is, the name of this picture is? Anyone on the chat that would like to say something about this picture?
Nothing.
Nothing? Okay. The name that goes behind this picture is called The Day the Earth Smiled. And what happened is, I think NASA or ESA made out announcements all across the world that on 19th of July 2013, everyone on the Earth was to look up at the sky and wave and smile. And what happened on that day was Cassini took a picture of the Earth with all the people waving and smiling. So that's why it's called the Day the Earth Smiled. So I think that's pretty good. I actually remember that day because I think I went outside and waved my hand and smiled.
It's quite amazing if you look at that bright ring as well.
Yeah.
To have all the rings have that very bright ring, that further out ring. It's quite an amazing photo.
Yeah, it is an amazing photo. I've just zoomed into that planet, to that photo of the Earth, and you can actually see when you zoom in, you can see the Earth and the Moon there. I think, it's quite a remarkable photo that you can actually look at those, this kind of Moon-Earth system there. We almost call it a binary planetary system, actually. So, and that's the view from Saturn of our planet. Okay, here is the sizes of our planet. So they're not in distance to scale, but they're scaled in terms of the sizes. So we've got all our planets there, including a few extras like Pluto. What's remarkable about this, so it's a true size of Sun, planets, but all the planets can actually, except Jupiter, can actually fit inside Jupiter. So Jupiter is a pretty large planet. So if you take all our planets, they could all fit in, even Saturn, Uranus, Neptune, and all the terrestrial planets could actually fit inside Jupiter. In terms of looking at the distance, here's a kind of a distance to scale. And so what I need to talk about here is astronomical units. So the distance between the Sun and the Earth is called 1 astronomical unit, and that's equivalent to something like 150 million kilometers. And if you want to get an idea of scale, what you can do is take that 1 astronomical unit and scale it to a meter. So we scale that distance from the Earth to the Sun to 1 meter. The Sun becomes the size of a marble. So, those marbles that we tend to play with when we were younger, that's the size of the Sun. So the Earth is a meter away, and the size of the Earth is actually thinner than the thickness of a piece of paper, and that's about something like 0.1 of a millimeter. So Mercury is about 40 centimeters away from the Sun on that scale. Venus is about 70 centimeters. The Earth, of course, is 1 meter away. Mars is about 1.5 meters. Then we have Jupiter, which is about 5 meters away. Saturn is 9.5 meters away. And Uranus is about 19 meters away. And Neptune's about 30 meters away. So you can imagine that's the size of our solar system to scale. Imagine the sun being a marble and Neptune being at least 30 meters away. If you want to imagine what 30 meters is, roughly, it's I think about the length of a netball court. So you can kind of put the sun as a marble on one end of the court, and the distance to Neptune is at the other end of the court.
Antony, if I remember correctly, isn't there a scale version of the solar system out near Whitby?
Yes, there is, yeah. Mark Reading runs a Whitby solar system scale, so he's got it all on a park out there.
Yeah, because I remember when it was originally kind of set up, it was quite impressive actually physically seeing it.
Mm. You can follow his page, actually. I think it's called the Whitby Solar System Scale or something to that effect. If you look up Whitby Solar System, I think you'll find the page.
Yeah, so I'll certainly add that in our directory.
Yeah. One thing I should mention also, it takes light 8.3 minutes from the sun to the Earth. So when we look at the sun, we're looking at it basically 8.3 minutes ago, and if the sun was to disappear, we wouldn't know for 8.3 minutes. And light travels at 300,000 kilometers per second. And the distance scale that we tend to use for the universe or the cosmos is a light year. And if you work it out at 300,000 kilometers per second, a light year is roughly 9.5 million kilometers, or 9.5 trillion kilometers. So that's the kind of scale we use. Now, if you want to go out to Saturn, I think it takes about 2 hours to the light from Saturn to reach the Earth. So when we look at Saturn, for instance, through a telescope, we're actually seeing it as it was 2 hours ago. Now, what I want to try to do is give you a scale of the stars. If you're in Wellington and we had one marble representing our sun, Alpha Centauri, which is our nearest star, about 4.3 light years away, is about on that scale that I had before of the Earth sun distance being 1 meter. Alpha Centauri would be 275 kilometers away. And if you work that out, that's the distance from Wellington to somewhere on the desert road between Wairau and Turangi. So you can imagine that these two stars, a nearest star, two marbles sitting 275 kilometers away from each other. And if you look at all the stars, there's only a handful of stars. I think it's something like 6 stars that will fit in the whole of New Zealand on that kind of distance scale. So again, I'm trying to impress that space is basically empty, and we've got this scattering of stars out there, but mainly emptiness out there.
Sorry, Antony, there was a question: is how long does a light take to get to Pluto?
It's about 50 hours, I think, from memory. So yeah. So when we look at Pluto, that's why when we send spacecraft up to like Saturn, like the Cassini probe, it has to be reasonably fully automated, because if Cassini, for instance, was in trouble, by the time it sent a message out, it would take 2 hours to get to the Earth. And by the time we responded on the Earth to send the message back, it was another 2 hours. There's a 4-hour difference there, and anything could have happened to the spacecraft in that time. So, one of these robotic spacecrafts have to be able to make adjustments and adjust to, anything that might be happening nearby, because there's no time for us on the Earth to actually give instructions back to tell it what to do. So here's an image of the night sky, sort of a dark, dark sky looking up. Now, if you looked up at our night sky and were able to count the stars there, you would count in the Southern Hemisphere probably maybe up to 6,000 stars. And if you counted the stars in the Northern Hemisphere at the same time, there are about 9,000 stars in our night sky that are visible naked eye. And all those stars that you can see are just part of this yellow circle here. So this is a sort of a picture of our galaxy, not an actual image, but an animated image of our galaxy. And you can see that little yellow circle in the middle, and that's all the stars that we can see in the night sky. So about 9,000 stars fit in there. So Sirius is the brightest star in our sky. That's about 8.6 light years away, and the most distant bright star is Deneb, and that's about 1,500 light years away. And the furthest star we can actually see with our naked eye is V762 Cas in Cassiopeia, and that's about 16,000 light years away. So it's a pretty large, bright star, probably a dying star out there, to be visible naked eye, 16,000 light years away. And its magnitude is about 5.8, just above the 6th magnitude limit. The other thing, when we look at our galaxies, all the planets that we've found to date, there's about just, I think, over 4,000 of them now. Most of those planets sit within a 300 light year radius of our sun. So you can imagine, we've found 4,000 planets, and there's a lot more to be found. Our galaxy is going to be literally full of planets. Our galaxy has something like 200 to 400 billion stars, and most star systems have planets around them. So you can imagine how many planets are out there in our galaxy itself. The structure of our galaxy is basically spiral arms. So you've got a kind of a barred structure there through the middle with a supermassive black hole in the center of our galaxy, and I'll talk a little bit more later. But essentially there's 4 arms, spiral arms coming out of our galaxy. Now, this is a picture for the Northern Hemisphere, but if you look at where our sun is, it's sitting on the Orion Spear, which is actually part of the Sagittarius Arm. And in wintertime, if you're looking up at the night sky, which is around now, the Milky Way sits right above us in the night sky. And we're looking at the center of our galaxy there during our wintertime. In our summertime, from the Southern Hemisphere, we're looking at sort of the outer arms of our Milky Way galaxy. So here's a picture a friend of mine took out of Bering Head here in Wellington. My friend's name is Edward Wilcock. He's a photographer, an astrophotographer, or landscape photographer, and he's done some amazing shots. So you can see here, this is the Milky Way. It's part of our night sky, and a lot of those stars there. With a camera, you can actually capture a lot more stars than naked eye. I wanted to point out this picture because there, about that point there, is where our supermassive black hole exists. And this black hole has mass of about 4 million of our suns. So it's sitting there in that part of the center of our galaxy. Now, as I mentioned, when we look at our Milky Way, we can see the light of the Milky Way there. But this light is actually the light from the inner and outer spiral arms of our galaxy. Like in this picture here, as we're looking at Sagittarius A, we're looking at the core of our galaxy. So we're looking at the inner spiral arms, whereas more towards the edges, we're looking at the outer spiral arms. But we can't actually resolve the stars anymore. All we're getting at this stage is the collective light of those stars in those other spiral arms. And that kind of makes up that glow of the Milky Way. And all the stars that we can see in this night sky, naked eye, is sitting as part of the Orion Spear where our sun sits. So
John Drummond was just pointing out that just above the hill there's the Milky Way Kiwi.
Yep. So I was going to ask a question about that. So that's Sagittarius A. So I was going to ask everyone, if this was interactive, I'd ask everyone if you could see a kiwi in that picture. And people will generally look around on the ground for a kiwi and can't see it, but there's a kiwi sitting right there. So this is what we call a galactic kiwi. So it's an asterism. Basically, it's a cloud of dust and gas sitting up there, which very much looks like, if I can show it to you, I don't know if you'll see my mouse coming up here, but that's the head, the beak of the kiwi, the head, and its body running around the back here, and its 2 legs running down here, these dark lanes are its legs. So that's what we call the galactic kiwi. So if you ever see pictures of the Milky Way, especially at the galactic center, you can always see that picture of the kiwi there. So next time you go out, have a look. You can actually see it naked eye. Like if you're in a dark sky and you look up, you can actually see the shape of this kiwi if you actually know what you're looking for. So here,
so it was quite interesting, that photo, because I mean, was that the Magellanic Clouds on the left?
yes,
And it
yeah, those are Magellanic Clouds here, which are satellite galaxies to our galaxy. So that is a large Magellanic Cloud.
There's a little meteor streak down the bottom.
Yeah, there's a meteor streak down there. So these are 160 something light years away, 1,000 light years away. So when we look at this large Magellanic Cloud, we're seeing it as it was 160,000 years ago. The small cloud's even further away, about 200,000 light years away. So we're seeing that as it was 200,000 years ago.
It's a really awesome photo, that.
Yeah, it is. It's amazing. Okay, here's a picture of our galaxy. And if we took the scale of our galaxy, if we want to kind of work out some sort of scale, it's huge. The galaxy is something like 100,000 light years across, maybe even bigger. People are quoting now like 120,000 light years across is the diameter of our galaxy. And, 100,000 light years across means it takes 100,000 years for light to travel across the galaxy from one end to the other end. So it's a pretty large object. But if you want to get some sense of scale, imagine our galaxy to the scale of Australia. So we talked about Australia before, that's 4,000 kilometers across. Our solar system, with the sun and the planets, is equivalent to 2.5 centimeters, so basically that. So you imagine all of Australia being our galaxy, our solar system is just 2.5 centimeters as part of Australia. So you can imagine now the size of our solar system compared to the size of our galaxy. And our Milky Way galaxy actually belongs to a group of galaxies called the local group. The Milky Way is the second largest galaxy in the local group, with Andromeda being the largest there, M31. And you can see Andromeda, well, definitely in the Northern Hemisphere you can see it, but here in Wellington, we can see it sort of, I think, around September, October time in the northern part of the sky, very low down. But I have seen it a few times, especially with a telescope. It's quite a remarkable object. It's a very large object, actually, to see through a telescope. But, these two large galaxies sitting in part of the local group. But the one thing also, there's about 30 galaxies in this local group, and Andromeda, Milky Way, and Triangulum down there are the three largest galaxies. Now, the Andromeda Galaxy and the Milky Way are on a collision path. They're actually traveling towards each other. Gravity is pulling them in towards each other. They're not due to collide for another 4.5 billion years, but they're actually traveling something like 110 kilometers per second towards each other, which equates to something like nearly 400,000 kilometers an hour. They're moving towards each other. So in about 4.5 billion years' time, they're going to merge. Well, actually, they're not going to merge because galaxies are still pretty much empty space. Is what they're going to do is they'll actually go through one another, and going through one another will cause some sort of activity and we'll get new star birth. But essentially, one galaxy will pass through the other, they will slow down, and they will come back, and they might oscillate a few times and eventually become one large galaxy in the night sky. So that's the fate of our galaxy and the Andromeda Galaxy. So here is what we call the Vega Cluster. The local group of galaxies that I talked about just now is being pulled into this cluster of galaxy. So there's a cluster of about 2,000 galaxies, on average maybe about 54 million light years away from us. And what I find remarkable is I can point a telescope and look at these galaxies and see that they're 54 million light years away, or of that order, 60 million light years away. And it's taken the light from that galaxy, those galaxies, 60 million years to reach us. And you think about it, the light from those galaxies left when there were probably still dinosaurs roaming our planet. And we just happened to catch it at the right time through our telescopes. And here is an image of basically our local group at the center there, and the other clusters of galaxies that are kind of nearby us. So you can see the Vega Cluster there, which is a pretty large cluster of galaxies, but there are also other clusters of galaxies sitting near us. Now, to jump back to this picture, which is again of the Vega Cluster, And there in the center of the picture is M87, which is the largest galaxy in that cluster of galaxies, with a supermassive black hole in there. In April last year, they managed to release a picture of that supermassive black hole. So there's M87 in the middle there. I'm just going to go back, actually. We can do that. Up here is the Marcanian chain of galaxies, which is quite remarkable to actually look at a pair of binoculars. This picture's upside down, actually, in the southern hemisphere. This chain will be below M87. But anyway, to get that picture, and whoops, we'll just put it back, wrong way. Here are some of the names of those galaxies there. Anyway, as I mentioned before, in April 2019, this amazing picture got taken, and it's of the supermassive black hole in M87. Now, they've had 8 massive telescopes taking data, basically, for quite a substantial period of time. And that data was collected. And that data is equivalent to half a ton of hard drives and 5 petabytes of data. Now, I don't know if you understand 5 petabytes data. We regularly talk about gigabytes of data. So, and then terabytes are 1,000 gigabytes is 1 terabyte. And we can buy hard drives now that are of the order of, maybe 4 or 5 terabytes. So, petabyte is 1,000 terabytes. So you can imagine, how many hard drives you'd have to buy to store that amount of data. But essentially it's half a ton of hard drives. Now I worked out that if you took DVDs, which are roughly 5 gigabytes of data, and without their covers, if you stack them all up, to get 5 petabytes of data, your DVD stack would reach up to 1.3 kilometers up in the sky. So you can imagine the amount of data sitting there. What's remarkable about this picture, as you can see there with the Sun and Pluto's orbit, it's right in, it's actually smaller than the size of that black hole. You can see that the black hole's rotating because it's got that curve of bright light there. So light is actually being bent around the black hole. So the back of the black hole, light coming out of that actually gets bent to the front also. Now, that Vega cluster is actually part of a much larger supercluster, which we call Mauna Kea, and that means immeasurable heaven in Hawaiian. And it's about 250 million light years across and contains well over 100,000 galaxies. The superclusters are the largest structures found in our universe. And here's a picture of, you can see the Vega cluster in the middle, and the Milky Way is actually lies on a spur that is lying just off the Vega cluster of galaxies. But you can see those strands or lines representing basically lines of galaxies moving out there. But what's remarkably amazing too is the Mauna Kea itself, all the galaxies seem to be moving towards this thing called the Great Attractor. So there's a flow of galaxies and filaments of galaxies all moving towards that. The Great Attractor is actually hard to see in visible wavelengths because it's actually sitting on the other side of our galaxy, on the plane of our galaxy itself. So it's not very easy to see. We can only see it, I think, using infrared light and get an idea of where it's sitting. So that's the Great Attractor. Now, if you kind of map up all our galaxies, you'll notice there's a kind of structure to these galaxies. And this is what we call the cosmic web. It's knots of superclusters, so you can see these bright knots in there. These are where the superclusters exist. And you can see these lines that move between the superclusters or between the knots. And these are filaments of galaxies. So basically you've got these large filaments of galaxies moving or attached, connecting one supercluster to another. And in between these regions are these huge empty voids that are devoid of matter almost. Very little matter exists in these voids, and they're very desolate places. So if I just click on that. So there again is a picture of these knots and clusters. You can see the void sitting in there. So it's kind of like a spider's web, really.
So there's a question: is what
Sure.
what causes the voids?
Okay. Didn't really want to go into this, but very early in our universe, essentially we get this very high densities of matter, tiny, incredibly small amount of matter, smaller than a proton, but very high in density energy and very high temperature. And there's this principle called the Heisenberg uncertainty principle, which basically says that even though the temperature you'd expect it to be smooth, there's actually some uncertainty in that temperature of that initial primordial piece of matter that's smaller than an atom. So what's happened there is because there are these slight variations in the temperature of that primordial atom, when it expanded out, areas that were basically cooler than the average temperature actually became cooled out and became matter. And the areas that were hotter essentially didn't cool out till much later. So essentially the matter cooled out but left these massive voids in between. So as the universe expanded, these voids also expanded. So all the matter that's sitting there is really the cool parts of the universe when the universe was formed during the Big Bang. Now here's a picture which was taken, not a picture, but basically a map of all the galaxies and superclusters of galaxies. And this is based on a redshift. So you can see the different colors there. The red colors are the actual clusters of galaxies that are much further away. And the lighter greener colors and bluer colors are clusters that are closer to us. So when we look at our galaxy, you can see there, this is an actual picture or a map of all the galaxies out there, and you can see that kind of cosmic structure out there in space. It's all a result of that quantum effect of the early universe.
So another question popped up was, will the great attractor be on the hit list for the James Webb Telescope? And I'm sure you won't be able to answer that one. But
well, I don't know actually, because the James Webb Telescope is going to be looking more in the red and infrared, so maybe it can peer through the dust and gases of our galaxy and look at the other side. And who knows? I don't know enough about the James Webb Telescope and what it can do. You basically need telescopes of different wavelengths to be able to look through the Milky Way to see the other side of it. And James Webb being kind of more on the red infrared side. And you need infrared because basically the visible light from the early universe has stretched out, so it's actually stretched out into the red part of the spectrum. And that's why the James Webb Telescope is looking at the red part of that spectrum to look deep into the early parts of the universe.
great, thanks.
So here's a video which basically describes what I've just talked about. So hopefully you'll be able to see it.
It's just the audio isn't coming through there.
Isn't it?
No.
Okay, let me just stop that. Whoops. Do we have a way of figuring that out, James? Because it's playing on my laptop.
What's the volume like on your laptop? Maybe if you just...
It's about 75%, so it's quite high. Can you hear anything at all or not at all?
Not enough to decipher what it is. I think...
But you can hear something.
Yeah, I think what it is because it's coming out the speakers and then going into the microphone. That might be the issue.
I thought it would play directly to you there.
That's what I would have thought as well. Yeah, unfortunately.
Okay, let me have a quick look. I don't think I can change any settings. Just have a quick look to see what the audio settings are.
Yeah.
Thing I can do there. Mute. No, I can't see anything obvious. I'll try that, see what happens. Just let me just play that again.
No, it's still the same.
Okay. All right. Probably I won't play it then. We'll just move on. But you can find this video on YouTube. It's a nature video.
Yeah, if you send me the link, what I'll do is I'll pop it onto the Facebook group, and people can have a look at it there.
Okay, yeah, fine. Let's do that. I just need to move forward. Okay. Right. Now, one thing about our universe is we call it the observable universe, but we actually don't know what the size of our actual universe is, because the light from the universe is, the universe has only been around for about 13.8 billion years, and the light from the early universe is just reaching us from those to us from that early part of the universe. So there's a kind of bubble that we can see, because when we look back out into space, we're actually looking back in time. If we're looking back in time, we're looking back to that early part of the universe. And so that is kind of like our boundaries, or further back, and the James Webb Telescope will be trying to look further back again, but we're essentially hitting a barrier there where we can't see anything further anymore. And that's kind of the bubble that we live in. Now, this bubble has a diameter of about 92 billion light years. And the reason for that is because it's expanded over that time. So you'd expect if there was no expansion, maybe that the bubble should only be about 13.8 billion light years in radius. So you double that, that will give you the diameter. But because the universe has expanded over time also, it's now sitting at 92 billion light years. But you can see there on that slide of mine, there are areas that we obviously can't see outside. So we're sitting in that middle circle. We've got two other circles there for region A and region B. So they're their own bubbles. So in this case, there is some intersection between the bubbles, but there are areas of the other bubbles that we can't see at all because light basically hasn't reached us from that bubbles. So that's really the explanation. So who knows what the size of our universe? It could be pretty big, it could be infinite. But because light only has taken only 13.8 billion years to get to us, we can't actually see beyond that point, essentially. But the other thing that's happening too is because the universe is expanding and actually accelerating in its expansion, everything is going to move apart. And in fact, we're going to see less and less of the universe because we're going to see these far distant galaxies that we can see now eventually moving away from us, moving faster and faster and going into the red and eventually just disappearing out. So even though our bubble is growing, everything in our universe is actually expanding out much faster. And so we're actually going to lose the galaxies that are on the edge, that we can see on the edge of our bubble. And that's purely because of the expanding universe. Now, what's making that universe expand and accelerate? Here's a diagram. So there's this thing called dark energy, which is actually just pushing the universe and it's causing it to accelerate. And in terms of energy density of the universe, dark energy represents 73% of our universe. There's also a thing which I haven't talked about, which is dark matter. And there's actually 6 times more dark matter than ordinary matter out there in the universe. It's matter that exists out there and we have no idea what it is. All we know about it is it does have a gravitational effect. So it does affect clusters of galaxies. It affects how our Milky Way or galaxies rotate, holding everything in to the galaxy. If it wasn't for dark matter, our galaxies would fly apart. So, but we still don't know what it is. And really the only, in terms of the universe, less than 4% of our universe is the matter that we know about, which is basically hydrogen and helium, the gas that's out there. And that 4%, there's less than 1% of that is actually in terms of stars and neutrinos and heavy elements. So you think about it, our stars and everything we're made of represents an incredibly small percentage of our universe. So in some sense, matter is really an anomaly in our universe, whereas our universe is really made up of dark matter and dark energy. So, we're some sort of remnant of our universe. Now, this is another picture that I absolutely love. This is called the Hubble Extreme Deep Field. This is an incredible image looking back 13.2 billion years. So when we're looking at this picture, I think I can see two stars there, but every single point of light there, apart from those two stars, is a galaxy. So you can see the galaxies closest to us, they have structure, they have spiral galaxies or elliptical galaxies. And as you move further into the picture, you can see these tiny dots of light and their galaxies way out in the distance. And there's a kind of the early, there's a kind of an evolutionary history here in this picture from the early formations of galaxies, which are these kind of irregular galaxies, and they merge into form bigger galaxies. And so you can see the kind of history of the universe, and the galaxies that are closest to us represent the kind of galaxies of the more recent time. So in this picture, there's something like 5,500 galaxies. As mentioned, you can see the evolution of galaxies in there. Now, to get that picture actually took about 2 million seconds of exposure. That's equivalent to 23 days of exposure that Hubble took of that one piece of sky over a 10-year period. Here's that picture there. You can see that tiny square in the middle of that picture next to the moon. That is the area that Hubble's taken. So you see it's an incredibly tiny area. That area represents something like 1 in 32 million parts, 1 part in 32 million. So if Hubble was to repeat that for every part of the sky to get that same image for every part of the sky, it would take Hubble over 1 million years to do that. And when you count up all those galaxies looking back in time, there's something like 2 trillion galaxies in our observable universe when you look back in time there. Something also remarkable about our universe, which this is a separate talk actually, there's a whole talk in this, and that is that our universe appears holographic in nature. So you could talk about holograms, but basically holograms is like a film, and you project a light through it, but it gives you a 3D image rather than an image on the screen. So our universe seems to be based on information that's sitting on some sort of surface, and that's information on that surface gives rise to our universe and gravity within our three-dimensional universe. So holograms are 3D images based on the 2D surface, and all the information is stored on the surface. And the thing about holograms themselves, if you take a small part of a hologram, you can actually form the whole picture again, but just with a less resolution. So in terms of you have a hologram on a piece of glass and you're shining a laser in it to get your 3D image, if that piece of glass breaks, and you just take a piece of the actual remnant of the hologram and shine a laser through that, you can actually get practically the full image back again, just on a less resolution. But what's remarkable about this is, well, it kind of shows that this holographic principle is kind of different form of reality for us. And it can actually be used because in this diagram here, you can see this kind of surface, which is where the information of our universe exists. And if you actually look at some of the theories, like if you look at hot radiation on that surface, you can kind of map that to the entropy of a black hole within that surface. So in the volume of this inside is the entropy of a black hole. So you can actually calculate the entropy of a black hole by calculating the hot radiation on the surface. And similarly, again, particles or fields, particle fields that exist on the surface, you base your calculations on the surface, that gives rise to superstrings inside your bulk, what they call the bulk, or the space inside the volume inside the universe itself. So there's this remarkable feature about our universe that seems to say that, you know, information is existing on some sort of surface. It's kind of a mathematical surface, but the information is sitting out there. And the universe that we actually see and perceive is really a projection of the information on that surface. So here's basically, you know, this our 3D universe could actually be a holographic projection of a 2D surface somewhere out there. And it's all based on mathematical theory, but there seems to be this nature that exists of our universe in this holographic nature. And if you talk about black holes, this theory actually came from black holes, because they talk about black holes, like things fall into a black hole, where does that information go? And people like Hawking and others worked out that the information, you know, there's basically a law of conservation here. You can't lose information in the universe. So what happens there is information actually ends up sitting on the event horizon of a black hole. And that's where this holographic theory comes from. All that information is conserved on the surface of a black hole. So in some sense, our universe could be like, you know, we're sitting inside a black hole with the information on that surface of that black hole. Anyway, that's a whole different talk. I just wanted to talk about this because it's important to what I want to say now. This is looking at the microscopic world now, about more to do with quantum theory. And there's a thing like particles where particles can have a property called spin. You can put two particles together with this property of spin, one spin up, one spin down, and you form a kind of a system. And this is what they call entangled particles. So there's a kind of a connection between these two particles in their lowest energy state. And what you could do with these two particles is you can separate them long distances. And if you flip one of the particles using a magnet, say, and change its direction of spin, the spin of the other particle immediately changes too. So what you can actually do is pull these particles apart so far. And in fact, you know, one of the theories that Einstein came up with is information can't travel faster than the speed of light. But here, this kind of almost disproves Einstein's theory. It doesn't, you know, when we talk about information in general relativity, that all works well. But when we start talking about the quantum world and quantum entanglement, basically there's an immediate effect here where you change one, immediately affects the other. And they've done this experiment many times in the lab. You can see this effect going on. They've done it between, I think, from the Canary Islands to the mainland. And you can see this instantaneous change in the particles. And the Japanese, more recently, I think a year or two ago, did the same experiment, putting one particle on board a spacecraft and one particle on the Earth, a distance of 1,200 kilometers away. They flip one particle and immediately flip the other particle. So there's something fundamental about our quantum world that we don't understand, something very fundamental about our universe that has to do with quantum entanglement.
I always love Einstein calling it spooky action at a distance.
That's right, yes. But what's remarkable, some of the theories that are coming out today talk about this bounding surface again, and they're talking about the quantum entanglement of particles on that surface, or the information on that surface. And that quantum entanglement is what gives rise to our space and time in our universe. So that quantum entanglement on that surface is what being projected is actually giving rise to space and time. Destroy that quantum entanglement on that surface and you effectively destroy space and time inside the bulk of that universe. So there's a lot of work being done in this theory now, and it seems to be working. I mean, there's mathematical proofs. It's not perfect. There are still some issues with it, but it kind of brings in quantum theory, holographic nature of the universe, and general relativity all together. So this may be a way to basically what they call the theory of quantum gravity, explaining quantum mechanics and general relativity at the same time, because these two theories are basically incompatible with each other. So we need a new theory which we call quantum gravity. So, you know, who knows? Our universe might actually have this very weird structure of quantum entanglement on a surface somewhere. It may be talking about infinity, but what does that really mean? And everything inside with space and time and matter is really a projection of that information on that surface. So, just jumping here back to that picture of the universe. Now, we're all part of the universe. We're made up of particles formed in the Big Bang and the elements formed in the cores of stars. We can't look from outside of the universe. We're actually part of it. So in some insignificant part of the supercluster of galaxies called, supercluster of galaxies called Mauna Kea, on a spur that's sitting off the Vega Cluster is the Milky Way galaxy. And in that Milky Way galaxy, there's a yellow star, our sun, with a system of planets. And on one of those planets, a small pale blue planet, life actually exists. So what we can say is that at least in this part of the universe has become self-aware of itself. Each and every one of us are part of that universe that is aware of itself. So the fact that we're looking out at the universe, we're beginning to grasp something about our universe is telling us that the universe is becoming self-aware. Just in this part, who knows, you know, we only know about life on our planet in this part of the universe. So at least we can say that this part of the universe is becoming self-aware. So here we are looking up at the stars and understanding our place in the universe. So thank you for listening.
There are trillions and trillions of galaxies out there, and you know, I think what if we look at what's it called, the Fermi paradox? There's just got to be life elsewhere, and it's a case of such long distances. It's, are we ever going to find it or not?
Yeah. I believe we'll definitely find life at some point in time, maybe in the next 5-10 years, who knows, because all we really need to look for is a signature of oxygen or ozone sitting on a planet somewhere, and that essentially oxygen is made by life. Our planet, when it was first formed, had no form of oxygen. It was eventually the bacteria that created the oxygen that gave us the ability to have higher forms of life. So, but that's our knowledge about life that requires oxygen. Who knows what life really is? I mean, it could take various other forms. There is actually life on our planet that doesn't require oxygen to survive. So, and definitely, they're estimating something like maybe Earth-sized planets that might have life on a galaxy. They're talking maybe about 50 million Earth-sized planets.
Yeah.
So how many of that would actually have life? But as I explained before, there's a huge distances between the star systems. So whether we actually, the limiting factor is the speed of light right now, unless we find some way of traveling faster than light. I don't know whether we'll ever visit some of these worlds. Well, definitely not in my lifetime.
Yeah, but as you say, I think it's not too far until we discover life, and it might not be life like aliens coming down and things like that, but certainly we've just found out in the last sort of month or so that Pluto looks like it's got a liquid center, and it has since its formation.
Exactly.
We have Enceladus out there, and a couple of the other big moons around Jupiter and Saturn, and they definitely have water there and all the ingredients needed for life. So that's looking quite good. And of course, we never discount Mars as well. Just recently, we've had that photo of the ice and the craters. Whatever's going on underneath that, there could be life there as well. So I think when we find life, it's probably going to be that microscopic life within our neighborhood. But for me, that's just as exciting as little green men dropping out the sky to visit us.
The thing is, you never know with Enceladus and Europa, for instance, because they've got warm oceans, right? They're talking about oceans, at least being 20 degrees. They'll be under very high pressure. But, if you've got warm oceans, you can have reactions taking place. Who knows what can form there? And who knows what evolution can produce in that kind of environment. So it'll be really interesting to see one day if they manage to get to Europa and drill a hole and see what's in there.
Yeah, I'm hoping. I know that one of the missions has been approved to one of those moons. I think it was Europa.
Yeah, I think the Europa Clipper, which they're going to send at some stage, and I'm not too sure whether that's going to be drilling a hole in the ice, but they're definitely preparing a mission. The thing with that layer of ice, I think it's something like 2 kilometers thick, so they actually have to drill quite a way down. The warm ocean, but then the ocean is actually, a few thousand kilometers, not thousands, but but definitely hundreds of kilometers deep. Unlike our ocean, which our ocean's deepest part something like 4 kilometers deep, whereas places like Europa and Enceladus, you're hundreds of kilometers of ocean down below.
Yeah. So, what is exciting you the most recently in astronomy?
Well, my background, not my background, my interest is in cosmology. That's why I talked about the holographic universe and quantum theory, because it's kind of all related, how particles are formed in the Big Bang. The fact that, there are flaws, even though we have this standard theory of particles, there are some flaws, like dark matter. We have no idea how to fit dark matter into, there are theories out there, but no one's actually found a dark matter particle and decided, what it is. So there's still a lot of controversy around that. And but it's all important. I mean, understanding the structure of particles and how they came about is very important in understanding the structure of our universe. And again, the fact that this holographic principle of our universe is really remarkable. And why is it that way? In fact, there's a nice YouTube video out there, which you have to take with a grain of salt, but it's called What is Reality? I'll send a link to that too. But it's quite remarkable. It takes all into account about the holographic universe, pixelation of the universe, meaning the universe is pixelated. It's not continuous. There's the smallest amount of space you can have. There's the smallest amount of time you can have. Time can run backwards and forwards, but for some reason, we need it to go forwards. But there's nothing, all the laws of physics can run backwards equally well as they can run forwards. So there's still a lot we need to understand about the universe. And that's what I find really exciting every time we make new discoveries about the universe.
I found, just recently, in the last sort of 5-10 years, I mean, the discoveries that we've made have been quite astounding. If you have a look at old Michio Kaku and his string theory, and how so much of that is also coming about now, sort of being proven or being suggested to the very...
My theory that I prefer, actually, that's I think is more plausible than string theory, is called loop quantum gravity. So if you want to look that up, that's really quite interesting. It talks about space and time being discrete, whereas string theory kind of expects space and time to be continuous. Whereas to me, it makes more sense when you talk about particles having quantum properties. So why won't space and time have quantum properties also?
Yeah. Oh, maybe we'll get you back to do a talk on that, the quantum side.
I'm happy to do that. We can talk about the holographic universe.
Because Ben Cullen pointed out that the answer to quantum gravity is simply 42.
Yeah.
Which I wonder if everyone got that. But Antony, thank you so much for coming and chatting to us and taking time out to have a chat to one of the newest societies out there. It's been a real pleasure, and what a fascinating talk. Thanks so much.
You're welcome.
We really do appreciate that. So,
if you want, and if any of you have got questions and want to fire them, send them to James, and James can email me or send them to me, and I can hopefully be able to answer some of them. Yeah, but definitely keep in touch, and we should kind of do things more together actually between societies, and this world of using Zoom and YouTube. I think gives us more possibilities and stuff.
Well, especially that's our aim here, is to sort of foster this communication between all the different societies, so that we get to know each other and see what people are talking about. So I think that's a fantastic thing. With that's come out of this COVID, is that people are more receptive to things like Zoom. So
thank you for inviting me, by the way. I really appreciated that, and I really enjoyed talking. I can't see the audience. I have no idea how many people were there, but hopefully
we'll have a look. We're sort of roughly about 20 odd people, but like I say, we'll probably get quite a few more sort of watching tomorrow as well.
Yeah.
So let me just pop on here and just say, if you hang on there, Antony, for all of you out there in internet land, thank you very much for attending. Like I say, don't forget that we've got Fraser Kane on Sunday. I will be posting more information about that in the next couple of days. And thank you everyone for attending. And I'll end the stream on YouTube now, and I'll chat to you a bit more.
Okay.